Okay, first problem. So a tow truck pulls a car 5 kilometers with 3 stick figs, 5 kilometers along a horizontal roadway using a cable having tension inside of the cable of 850 newtons. How much work does the cable do on the car if it pulls horizontally? Okay, what information do we have in the problem? Come on. Yes, Ahmed. Second, what is the degree? 0. The degree is 0 or the angle is 0. Why? Because the tension, apparently, if it's pulling horizontally and moving horizontally, that means what? They are parallel together. The force and the displacement are parallel, which means the angle is 0. What else do we know? Come on. Force, how much? And what's the last thing we know? Distance or displacement, 5 kilometers needs to be switched to what? Meters. Okay. So what's the equation for part A? W equals. Remember, there are two equations for work. One is the first one I taught you, and the second one. Which one are we going to use here? Exactly. So work of tension equals force of tension times displacement. Sorry, times distance, I guess, times the cosine of theta. Okay. So force of tension is 850 times 5,000, because it needs to be in meters, otherwise things are not standard, times cosine of 0 degrees. What's the angle? Sorry, what's the cosine of 0 degrees from the cast rule? Right here. 1, a positive 1, which makes sense because it has to be a positive work because the force and the displacement or motion are going exactly in the same direction. So that's plus 1, which means all we have to do now is multiply 850 times 5,000. Okay, well, 0, 0, 0, 0, 4 zeros, and 85 times 50 is 400 and 425. Yep. And what's the sig fig situation? Well, the sig fig situation is 850 has how many? 850 or is it 850.0? 850, so that only goes to what? 2 sig figs, even though that the angle is 3. Sorry, not angle, I mean the distance. So we need to make this into 2 sig figs in joules. So that will be what? 4.3 times 10 to the 6 joules. Or 4.3. Does anyone know what's 10 to the 6? It's a million. What's the scale? In case you were ever asked. Million rhymes with or starts the same way that yeah, million, but what's the, is it kilo or mega? Yes, million is mega. So 4.3 megajoules. Huge amount of work. Yeah, why? It's a sizable force, 850 newtons, and it's being acted over 5 kilometers. So that's a lot of energy burnt. Okay? All right. That was part A. That's all there is to it. Okay, what's part B? If it pulls at 35 degrees above the horizontal. Oh, sorry. Technically, that's also a part of, part A as well. What's the only thing that could change here, or that should change here? The degrees. So it's exactly the same amount. Sorry, I mean exactly the same kind of work, but now the cosine theta will be cosine of 35 degrees. Okay? So, all right. So for part B, we're just going to say dWt equals still 850, still 5,000, but now cosine of 35 degrees. Okay? I'll get my calculator right up. 850. Oh, let me do the cosine first. 35 cosine times 5,000 times 850. Obviously, we expect what? Less than 4.3 million because now the angle is not 100% with the motion. Yep. If I play with the exponent, yep, there you go. So it's 3.48 times 10 to the 6, or 3.5 times 10 to the 6 joules, or 3.5 megajoules. Mega. Okay, what's next? How much work does the cable do on the tow truck in both? What? Hold on. How much work does the cable do on the car if it pulls? Sorry, say that again. Oh, so we're done, or no? How much work does the cable do on the tow? Oh, tow truck. Sorry, everyone. Yes, my bad. So, the tension is extending between both, right? Between the car and the tow truck, right? But here's the, I mean, okay. So let's just sketch a quick diagram here. So in the original case, it was like this: the tow truck, the car, and it was like this. So on the car, if this is the car and this is the truck, tension is pulling on the truck this way, right? And tension is pulling on the car this way. No problem here. That was the first case, everyone. That was the first case. The second case, still like this. Here's the car. Here's the truck. But now the what? There's an angle, right? However, this one's still moving which way? This way, right? So again, no problem. This is also 35 degrees here. But this is also what? Yes, exactly. So this is 35 degrees because of the Z pattern. And the tension is going this way, and the tension is going this way. Is it making sense so far? As far as the diagram is concerned, both the truck here and the car were moving this way, right? So motion was this way, and motion was this way. So my question to you is this: if you look at this one, how is the car? How is the tension on the car and the motion going? Against or together? Come on, together. Those two are together. So what's the angle between these two? 0. But what's the angle between these two? Exactly. So that means what? On the truck, tension is doing positive or negative work. On the truck, the tension is directed against the motion, which means this force is doing negative work as far as the truck is concerned. But with respect to the car, this force is doing what work? Positive, okay? However, here, same thing. Here, are those two technically going against or together? Those two together. How about, sorry, how about those two? Against, right? So that means what? In this case as well, the T here, the T here is doing what kind of work on the car? Positive or negative? Positive. However, here it's doing how much work? Sorry, doing what kind of work on the truck? Negative. But my question is, what's the angle between this vector and this vector? Come on, think of your geometry angle stuff. How would you figure out? I mean, this is easy. This is 35. This is 35. How about between here? If you put this one here and you make them tail to tail, how much would this angle be? Josh? You can just tell me the process. No need for the number. Yeah, obviously, one of two ways. Either what? Either say, hold on a minute. How much is this angle? Well, I can see that. Can someone tell me how much this is? Well, how much is the full thing? Always. What's a protractor? Exactly. A protractor is 180. How much are we subtracting? 35. So cosine of this angle, which we know cosine of any obtuse angle is always what? Cosine is cosine of any obtuse angle. So the cosine of any angle in quadrant 2, like here, is always what? Negative. Exactly. So to Josh's point, why can't we just do the cosine of 35 and then slap what next to it? A negative. It's gonna work out either way. I'll prove it to you. What's 180 minus 35? Come on. 155. So 145. So here it is. 145 cosine is what? Oops, sorry. Let's negative what? 819. How about the cosine of 35? It should be the exact same number, but with a what? With a positive. So 35 with a cosine. Yep, exact same thing. So either way is correct because there has to be a negative involved. Okay, so we can say what? We can say here that for the next part is WT on truck is equal to what? Negative WT on the what? On the what? On the car. We can just, it doesn't matter. Remember, the minus is just what? The minus is either way. But you're right. But because I want this one to be negative, I put negative with the positive one. That's all. Okay, what's part C? How much work does gravity do on the car in part A? Either way, here or here, gravity points which way? Straight down, which means if I just add it to the diagram, FG, FG. What's the angle between this FG and this motion here, or FG and this motion here? What's the angle? Angle. Angle is perpendicular 90 degrees, and the cosine of 90 is by default always what? 0, because it's exactly in the middle between the positives and the negatives. So that means we can just say this. Since FG and motion are perpendicular, WG is equal to 0 joules. Done. Okay. All right. Let's do the next question. Two tugboats, as far as you're concerned, two people, are pulling on a disabled super tanker. So basically, two forces are acting on one single object. Each tug exerts a constant force of 1.8 times 10 to the 6 newtons, one at 14 degrees west of north. West of north. I remember the old Nelson textbook used to use that notation. What's west of north? Northwest, exactly. So north, 14 degrees west. And the other one is 14 degrees what? East of north, or north, 14 degrees east. The question is, they both pull it, like the whole pulling of the motion is 0.75 kilometers or 750 meters to the north. Of course, to the north, because if you pull west and you pull, if you pull west and one other person pulls east and you're perfectly symmetric, the only way the object is going to move is where? Exactly in the middle between you two, which in this case happens to be perfectly north. So towards the north, what is the total work done on the super tanker? How many forces do we have? Two. Each one does its own what? Does its own work. So what do we need to do with the works? Get each one and then what? Add them up. But do you think the works are going to be perfectly identical? Symmetric, I mean. Think about it. You are pulling this way. Someone else is pulling the other way. Both of you are pulling exactly the same degree, and both of you are pulling exactly at with the same force. Do you think you both are going to do the exact same amount of work? Yes, you will, because the force is the same, the distance is the same, and the angle is the what? Is the same. It just happens to be what? Mirror image flipped, right? Which really doesn't matter because it's got to be the exact same thing, mirror image. Okay, so let's just sketch a quick FBD. What's up? No. Okay, here's the thing. Is either one of them going against motion? See, they're just mirror image, but they're both going what? With the motion. Do you see what I mean? They're both flipped, but neither one is flipped against the motion. It's not like the truck problem. Okay, that's gonna be the helping symmetry factor, is that both of them are going with motion. Okay, so everyone, yes, hello? Hello. Go ahead. Go for it. Is the event a full day? It's a full day. Oh, nice. Yes. Wait, wait, teacher dunk tank? What did we, what? All right. Well, you still have final marks to be released, so be careful. Okay, so quick diagram. Here's the tugboat, everyone. So I guess this would be the east-west axis, and this would be the north-south. All right, so let's sketch two forces. By the way, do I need to sketch? Okay, do you think this got to be a side view or a top view? Yeah, do we really need the side view? I mean, we still know what force acts downward, gravity, and it's a tanker. It's in water. So what acts up as well? By the way, do you know what we call normal force when the liquid is involved? Buoyancy, force of buoyancy. When something is buoyant, that means what? It floats in the what? In any liquid. Okay. Obviously, we don't need that because it's neither moving up nor they're moving north. So you need a top view. Everyone remember, sometimes you need a side view, sometimes you need a top view or a bottom view, but I like the top view better. So this is north, and this is east, and this is actually I don't like arrows here. I like to put them with the vectors. My bad. I mean with the forces. West and south. Okay, where's my first force? Which direction? West of north or north 14 degrees west. So I'm just gonna do. Oh, my bad. Draw. Okay, I'm just gonna go black. All right. I guess. Wait, north, west of. So north 14. So yeah, it's only 14 here. So like this. 14 degrees this way. Is the other one perfectly a mirror image? Yes, it is. And this is the motion direction. Both of these forces, do they do negative or positive work? Right there, without even doing any calculation. They both have to do positive work because they are both pointing roughly where the motion is. Perfect. So now we're ready to do what? Oh, let's call this force 1. And let's call this force 2 without any numbers. Okay, let's do the calculation. Actually, we do not even need this part of the diagram because everything is pointing up north. All right. So work of force 1 equals force 1 times delta D times cosine of theta. All right. How much is force 1 or force 2 for that matter? How much? Each force is exactly how much? 1.8 times 10 to the 6 or 1.8 million newtons. So 1.8 times 10 to the 6 times 6 times. What's the distance? 0.75 kilometers, but it needs to be what? Meters. So if you multiply by 1,000, you get 750. Times cosine of, if I move this guy here, tail to tail, yep, it's 14 degrees between the two. Yeah, that makes sense. So we just now multiply these two, and that will give us 14 degrees. Let me clean first. 14 degrees cosine times 750 times 1.8 exponent 6. Boom, that's the answer. A huge amount of work, as expected, of course. What's the specific situation in this problem? 2, is it? 3, oh, 2 because of the angle. You're right. So 1.3 times 10 to the 9. Does anyone know what's 10 to the 9 in a prefix scale kind of way? Kilo, mega, giga. So 1.3 times 10 to the 9 joules. Sorry, yeah, 10 to the 9 joules, which is 1.3 gigajoules. But that's only the work of how many forces? One force. What do we need to do with it? Add them, because we have to double it, because basically we have two forces. Sorry, say again. Yeah, exactly. Yeah. So the entire work done on the tanker, super tanker, is 2.6 gigajoules. Yeah, you're right. So I'm just gonna do it here. So W total is equal to 2 times 1.3 times 10 to the 9, which is 2.6 times 10 to the 9 joules, or 2.6 gigajoules. 2.6 gigajoules. Oops. Happy birthday. And you as well. Okay? Just basic stuff here. Any questions so far? Good? Okay. Okay, let me skip this one because it has circular motion. I want to do it after, like when next time we do a university problems. Ah, yes. Okay. Come on, focus. Okay, so a 1.5 kilogram book is sliding along a rough horizontal surface. Because it's rough, there must be what? There must be friction. Okay. At point A, it is moving at 3.21 meters per second. And at point B, it has slowed down to 1.25 meters per second. Question 1. How much work was done on the book between points A and B? Between points A and B. Okay. They're asking for work. What's the equation for work? As usual, force times distance times cosine theta. Do we have any force information here? Do we have any distance information here? What do we have here? Remember, what? Just look at the values. We have, what do we have first? We have mass. And what do we have here? We have speeds. So which formula of work are we going to use? What's the second formula of work? The one that does not involve force or distance or cosine of theta. Say again? Energy. Change in what? Change in energy. What kind of energy do you calculate when you have speed? We only learned two kinds of energy so far. Kinetic, exactly. So we have to say what? Work equals change in what? Energy. But what kind of energy? Come on. Kinetic. What's delta all the time? All the time. Change. But what's mathematically the formula? Initial minus final. Sorry. I should stop listening to you. Final minus initial. EKF subtract EKY. So EKI. Keep going. What's next? Come on, people. I know it's Monday, but come on. What's my next step? I'm literally just building up the math here. No more physics. What's the equation for EK? Come on. I know you don't have to memorize, but through continuous practice. What's half mass speed squared? Don't forget the square. So half mass VF squared subtract half mass VI squared. Oops, sorry. Hey, what's a common factor here? Or maybe two common factors. Half and m. So now I can start with the math. Equals half. What's the mass? What was the mass? 1.5 kilograms. And now I'm going to open a bracket and do VF squared minus VI squared. What's the VF squared? Which one is VF squared? 1.25, because it was the final speed, or it slowed down to it. So it came in the future. So 1.25 squared, subtract 3.21 squared. Sorry, squared. Okay. All we have to do now is just find out this number. By the way, do we expect this answer to be positive or negative? Did it speed up or slow down? Slow down, which means did it gain energy or lose energy? Energy was sucked out of the of the object, and that's what made it slow down. So let me just do the math here. So obviously, I'm gonna do the subtraction first. So it's 1.25 squared minus 3.21 squared. Yep, negative as expected. And then I'm just gonna multiply by the mass and then by half. So times 1.5 times 0.5. Boom, that's it, done. What's the sig fig situation so far? 3. So we need to cut this at 3. So what would the answer be? Negative what? 6.56 in joules. By the way, look at the question. Can someone read part A again? Who would like to read part A? Just raise your hand. Who would like to read? Ahmed, go ahead. How much? What does that mean as far as my final answer is concerned? About me expressing my final answer. Say again. So everyone, technically, because the question has what? Has what? How much? What does that mean? I need to say technically a therefore statement at the end. What is my therefore statement? Should it include a negative or no? Remember, everyone, when you ask for how much or magnitude or what was the third one? Magnitude, how much, or amount, you have got to use what? You have got to use a positive amount. I'm not going to change it. I'm just going to leave it up there, but I just wanted to comment about that. Okay? All right. How about question B? What are you given in question B? You're given the what? You're given the work. And what are you asked for? How fast is it moving at some future point? So are you being asked for VI or VF for the second phase? For the second phase. You're asked for VF. Okay, so everyone, we're going to do the exact same equation. But this time, instead of finding W, I'm going to find what? VF. My question is, what's my VI? What's my VI for the second phase? 1.2, exactly. Every phase picks up from the phase before it. So, part B, we go here. W equals, still the same thing, half M VF squared. How much work is there? Positive or negative? So what do we expect VF to be even? Faster or slower? Slower. Perfect. So, everyone, negative 0.75 equals 1/2 1.5 VF squared, subtract 1/2, sorry, 1.5. What did you say? 1.25 squared. Yes. Yep. Yes. Oh, there we go. Squared. Thank you. Okay. Let's clean up. So 0.75 equals what's 1/2 of 1.5? 0.75. Minus, I need to clean this up. Well, straightforward here. Let's do the exponent first. 1.25 squared times 1.5 times 0.5. There you go. Since we have 3 sig figs, let's keep 4. So I'm going to go with 1.172. How do I solve this? Remember, I'm trying to solve for the VF eventually. What do I do? Yep. Yes, what do I do? I need to move stuff around. So what do I move? Obviously, I'm going to move this one here and this one here. Oh, my bad. No, what am I talking about? I'm going to move just this one here. Yeah, sure. No problem. Okay, I'm going to move that one. So actually, just because I want to have enough space for the, let me just see what's part C. Okay, I'm just going to provide the final answer because I need some space for part C. So the final answer will be VF equals. Okay, so let's think about this. First, I'm going to have to move that one there. So it becomes what? Positive. So it's got to be negative 0.75 plus 1.172. So clear. 0.75. Sorry, 0.75 with a negative plus 1.172. And then what do? You divide by what? You divide by that, and then you square root. So 0.75. 0.750 meters per second. Does that make sense? Yes. Is it faster or slower than before? Yeah. 3.21 meters per second, went down to 1.25 meters per second, went down to 0.75 meters per second. It makes sense. When you're losing work, sorry, when you're losing energy or having negative work done on you, you are losing what? You are losing speed. Okay? All right, Ammar, what's part C? Exactly. So what exactly would I change there? Only one number. Which number would it change in the second line? Exactly. Everything would stay the same because I'm still shooting for the final speed and I'm still starting from 1.25. But now I'm what? I'm gaining work. Exactly. Or I'm gaining energy. So it's got to be positive 0.75 equals 1 half 1.5 VF squared subtract 1 half. You know what to do. I'm just going to squeeze this and lower it. Perfect. 1 half 1.5 1.25 squared. You know what? Let's mentally work out the final answer. What should we do first? Well, more or less the same thing as cleanup. So that means we're gonna. By the way, is this number, everyone, the same as this number? Perfect. So we have it. It's this one, but with minus as well. If I move it, it becomes what? But now it's being what? Added to this. Perfect. So all we have to do is add this one to this one. So we're going to do 1.172. Let me clean up first. 1.172 plus 0.75. There we go. And we're still going to do the same thing. We're going to divide by 0.75. And we're going to square root. 1.60. Okay. Those are very quick application. I'll show you how to do it. Okay, don't worry before you leave. Some typical kinetic energies. Okay, In the Bohr model of the atom, the famous hydrogen atom, the ground state, how many of you have heard of something called the ground state? Come on, people, you did chemistry. What's ground state? Anyone knows what ground state is? You either did it in grade 11 or you definitely got to do it in grade 12. Whenever you hear of a ground state, the ground state of any electron, the ground state of any electron is the amount of energy it has at the lowest energy level. How many people remember Bohr-Rutherford diagram from grade 10? What Bohr-Rutherford BR diagrams from grade 10? How do they look like? They look like what? Circles. Okay. The first circle is what we call the what? Ground state. It's basically the the energy level n equals 1. Okay, just so you know. Electron hydrogen has an orbital speed of 2,190 kilometers per second. That's how fast the electron is spinning around the proton in a hydrogen atom. Sorry, hydrogen nucleus. Question, what is the kinetic energy? All right, what's the formula for kinetic energy? A equals half. What do I need? The mass of what? The electron. Okay, I have it, 9.11 times 10 to the negative 31 in kilograms. Now, what do I need to do with the speed? I need to convert this to what? Meters per second. Well, it's already in kilometers, so I just need to multiply it by 1,000. Or, if you want to be smart about this, write it in scientific notation, 2.190 times 10 to the 3, and then add 3 more powers. So in meters per second, this would be this. So let me just squeeze and zoom in. I would. Okay, 2.190 times 10 to the 6 squared. That's it. We just have to evaluate this number now. Well, obviously, I would definitely start with the square part. So 2.190, whatever, exponent 6, square it, times 9.11 exponent 31 with a negative, please. 31 with a negative, times a half. That's how much kinetic energy the electron has while it orbits the what? The proton in the hydrogen nucleus. What's the sig big situation? 3. So 2.18. Okay. By the way, does that make sense? Of course it makes sense. We do not expect the electron to have a huge amount of kinetic energy, even though it has a huge speed, but it has a very small what? Mass. By the way, remember, that's actually a question in your quiz that I posted yesterday. It's not, is it always speed? Is it always mass? Is it both? You just have to make a decision. Okay, B, if you drop a 1 kilogram, let's say this weighs 1 kilogram or has a mass of 1 kilogram, and you drop it from a height of 1 meter, so roughly like this. Question is, how many joules of kinetic energy will it have when it reaches the ground? Right before it touches the ground. Because when it touches the ground, what's the speed? 0. No, we'll talk about immediately before. Okay, question for you. Is this kind of like a conversion of energy such a situation? Yes, at the beginning. Is it moving? But is it elevated? So when you, as everyone, if I'm holding it like this, is it moving? So EK is 0, but is it elevated? So does it have EG in it? Okay, release. As it goes down, what happens to the EG? It goes down. But what happens to the EK? It goes up. And right before it touches, what happens to the EG? It's practically what? 0. But what's the EK? It's practically what? 100% full. Exactly. So that means to know how much energy it has here, EK, you just need to know how much energy it has here, what? EG. Exactly. Because EK here used to be EG here. So we can say this. Everyone, we can say this for part B. We can say EK bottom equals what? EK at the bottom equals EG at the top. Yep. By the way, this is, everyone listen up. This is a common way when I subscript my energies. I always tell you two things. What energy is it? And where is it? What's the equation for EG? Three things multiplied together. MGH. M is 1, G is 9.8, and even H is what in this case? No, but what is it as a number? 1. You are dropping 1 kilo from 1 meter. So 1 times 9.8 times 1, which is what? What's 1 times 9.8 times 1? 9.8. So apparently it will have only 9.8 joules of energy right before it touches the ground. Done. Okay. Finally, is it reasonable that a 30-kilogram child could run fast enough to have 100 joules of kinetic energy? Okay. Forget that. The question is an assessment question. What are you given in the question? 30 kilograms, which is what? Mass. And also what? You're given the EK. What are you being asked to find? If you know the mass and you know the EK, what's the only left variable in the question? Speed. I need to know basically how fast can a child run if he has or she has a mass of 30 kilograms to develop or to possess 100 joules of kinetic energy. All right. So part C. EK equals 1/2 mv squared. 1/2 EK is how much? Come on. 100 joules or 100. Sorry. Oops. 100 equals 1/2. How much is the mass? All right, we need to solve for V. Okay, well, that's easy. Clean up first. 100 equals half of 30 is 15 exactly. V squared, which means V squared is 100 divided by 15. 100 divided by 15 is 6. 90, 2/3, 6.66666 forever. So 6.67, which means V is equal to the square root of this guy. What's the square root? 2 point something. What's the square root? Oh, right. 2.58 or 2.6. Is that reasonable? Okay, again, we don't really, have much experience with meters per second. We have a lot of experience with what? Kilometers per hour. Let's convert this to kilometers per hour. What's the trick? What's the magic number? Between three. My question is, are you going to multiply that by 3.6 or divide it? How many of you say multiply? Give me one reason that you're right. You're right. Why? Because you're going from seconds to what? Hours. You want to magnify. You want to magnify, you multiply. Done. So this number is 2.6 times 3.6. Does anyone know the conversion to miles? How many kilometers in a mile? Anyone knows? 1.6. Technically 1.609, but let's just say 1.6. By the way, I'm just trying to convert it to what? Treadmill speed. Because treadmills usually come in what? They almost never come in kilometers per hour. It's always miles. If you put a child on a treadmill and you put them on 6 miles per hour, do you think they can keep up? Just for a few seconds. Good question, though. You know what? I never thought of it that way. By the way, does anyone know what's a speed walking speed? Like if I'm walking like this, what's this? Do you know how fast this would be on a treadmill? No, this is 4. 4 miles per hour. 4 miles per hour is speed walking. Anything over 4, you actually need to start what? You start running, jumping. So that means what? Is this walking speed or is this kind of like jogging speed. This is jogging speed. But do you still think that a kid could jog at that speed even for a few seconds? Yeah, I mean, fine. By the way, 30 kilograms, which is like half of my mass, 66 pounds. Yes, they can. Done. That's it. What if it was 1,000 joules? Everyone, what if this was instead of 100, 1,000 joules? No way. Why? Because then the speed would be what? By the way, would it be 10 times faster? No, because there's a square involved. There's a square involved. It's not gonna be 10 times faster. It's gonna be faster, but not 10 times. Okay. Yes. So you divide 1,000 by 15, 1,000 by 15, which is 1,000 divided by 15, and you take the square root of this guy, which is this many times 3.6 divided by 1.6. Yeah, don't put, yeah. You want to put a treadmill on 18 miles per hour? That's insane. That's huge. Yeah. Probably no one would be able to keep up. Okay? Done. That's it. Okay, last question for today. Okay. A soccer ball with a mass of 0.420 kilograms is initially moving with a speed of 2 meters per second. A soccer player kicks the ball, exerting a what? A what? Constant. So the whole time his foot or her foot is with the ball, they are exerting a what? Constant, not variable. Constant force of how much? 40 newtons. In the same direction as the what? As the ball. So the ball was moving. Everyone, look at me. The ball was moving. They just caught up to it. And then even what? Kicked it backward or forward. They basically still assisted its motion. The question is, over what distance must the player foot be in contact with the ball to increase its speed from the moment of touching of 2 to the moment of release of 6 meters per second? Okay, lots of things here. What are those things? What things do we have in the problem? Come on. We have the mass of the ball. Okay, that's good. We have, how many speeds do we have? We have 2 speeds. We have the initial speed and we have the what? Final speed. When you have initial and final, what you can always calculate? Whenever you always have initial and final, you can get delta or a change, which is what we can calculate now. What? The delta EK of the what? The delta EK of the ball. But that still doesn't help us with the problem. The problem is asking us for what? Over how much what? Distance. Is there a relation between delta EK and work? Yes, it's the definition. So this is a 2-step problem. Get delta EK, take that number, and what? Do then the W equals F times delta D times cosine of theta. Okay, so everyone, step 1. I want you to write step 1. Step number 1. Delta EK. Okay, which is EK final minus EK initial. All right. Hey, let's do the equation again. Half mv final squared minus half m v initial squared. Again, what's a common factor? Both of them. Come on. Half and m. So the half is here. The m is 0.42 in kilos. So 0.42. 0. What's my final speed that I'm trying to build up to? 6. So 6 squared. And my initial speed I start from is 2. Great. Now I can know how much change in kinetic energy the ball had. So that would be half of 4. No. Mass is never in what? It's always in what? Kilos. So half of 42 is 21. So 0.21 times 6 squared is what? 4 squared is what? 36 minus 4 is 32. So let's see how many joules of change in kinetic energy it went through. 0.21 times 32. Yep, 6.72. What is that number? If it's delta EK, it's also what? It's also the amount of what? Work done on the ball. Well, we also have the force done on the ball. And technically, what's the cosine of theta? Is it cosine of 180 or is it cosine of 0? Did the player kick it against its motion or with its motion? With, which means the force applied and the motion were together. So that's a cosine of 0, which is positive 1. All right, so step number 2. Step number 2. W equals delta EK, which means force times distance times cosine of theta is equal to 6.72. Done. Now I have to solve for distance. So distance equals 6.72 divided by, what was the force? 40? 40 newtons times cosine of 0. I don't need brackets here, actually. Sorry. Yep, there we go. 40. Cosine of 0 is what? Positive 1. So I just need to divide 6.72 divided by 40. Point 168 in what unit? It's a distance, and it has to be standard meters. Do you think this is a good scale for that number? It's a small number. Maybe should be what? Centimeters. What would this be in centimeters? 16.8. Remember, in university, they will leave it up to you to choose the best scale. And it's based on experience as well as what's most convenient for this exact number.